right, welcome back, ladies and gentlemen. As you can see on the board here, we're in week 2, day number 4, and I am joined by our fantastic second grade teacher, Miss Stubbs.
Hello.
I invited Miss Stubbs here to talk to us today because her class, the second grade, all of you in second grade, won 3rd place at the SARSEF Science Fair this year, and I wanted her to talk about the project. But first, there's a couple of us in this room. Let's all give Miss Stubbs in the second grade a round of applause. Yeah, great work, you guys. That was fantastic. You kids did great. So, Ms. Stubbs, for those of us who are watching this who do not know what the second grade did for your science fair this year, would you mind explaining it to us?
Yeah, sure. So we tested unconventional cleaners. So we tested things like vinegar, Coca-Cola, soda, hot water, just hot water, using a rag that all of us used with soap on it, and things like that to see if they were good germ killers. Supposedly, we did this before all this happened, so it was a coincidence. And we found out that vinegar and like Coca-Cola and even really hot water just by itself seemed to kill really good.
That's excellent.
And we won 3rd place.
That was awesome. So kids, again, I love the fact that you second graders out there with your teacher did this experiment, and it is so, I guess, important, given everything that's happening. It's so relevant, yeah. And so can you say that again, Ms. Stubbs, for those of us who missed it? What are the things that your class found that killed germs the best from your experiment?
From what we could see, we forgot to do a test where we actually used a cleaner, but would eliminate most of what was on a kid's desk compared to a dirty desk was vinegar, which I've heard cleans anyway, Coca-Cola soda, you just had to wipe the stick off really good, and really hot water with nothing in it.
Hey,
for us, it worked.
That's great advice. So kids, if you are at home and you run out of all of your cleaning supplies, but you still have some vinegar or some really hot water, you know, that might be a good way to try to clean up a little bit. But we weren't testing these on viruses, kids. I think it was all bacteria.
We don't know what we tested it on. It could have been anything. As a teacher or someone, we're not allowed, we can't actually identify what grew on our plate. We might not have had either viruses or bacteria. It could have just been mold or things like that. Yeah. As a layman, we can't identify
we can't figure out.
But it eliminated
second
colonies.
grade, not a lab. Yeah, not a
It eliminated colonies from hundreds of colonies down to 23 colonies.
Wow. So the things that the little bugs and germs that you killed it really worked. So
something got killed. Yeah.
Excellent. So kids, anyway, that is a fantastic takeaway. And again, you second graders, we're all extremely proud of you guys. You guys did fantastic. So, Ms. Stubbs, do you have a joke for us today?
I do have a joke. Hold on. All right. What do you call a boomerang that won't come back?
I don't know, Ms. Stubbs. What do you call a boomerang that won't come back?
A stick.
Because you just threw a stick at someone. Okay. All right, that's cute. I really like that one. That's good. You gotta tell my. Oh no, my kids are watching this. Okay. Anyway, so let's go ahead and get ready for the pledge. Ms. Stubbs, if you wouldn't mind, please.
Yes. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Well, Ms. Stubbs.
Was I not supposed to leave it? Sorry.
Oh, no. You're definitely, you did great. Thank you so much.
Sorry.
So, Ms. Stubbs, thank you so much for being with us here today, and thank you for sharing. It was fantastic.
No worries.
All right, kids, let's get to our, week 2, day 4 of our online classes. See you online, kids. Okay. All right, this is life skills. So, for the past couple of days, we've been talking about paradox and how paradox, while seeming contradictory, paradox is something that occurs in all of our lives. And the great paradox, life being short and long at the same time, is largely what gives our lives meaning. Okay? Again, to review, what does that mean? Giving life meaning. Everybody has different loves and passions, and everybody's life has its own meaning, and it's different. For some of us, the meaning of our lives is the love that we have for other people. For some people, the primary meaning in their life is religious. They They love their religion, they love their God, and that's what gives their life their meaning. But in general, life is precious because of the fact that it is short and it is long at the same time. Again, the other day we said that if life went on forever, if you and I lived forever and were immortal, spending time with somebody wouldn't mean anything, because you would literally have all the time that ever was. And when something is unlimited, it becomes less valuable. Time in life is precious and has meaning because time and life itself is limited. And that is what gives it its value. So for day 4, what I wanted to talk about was, what do we do with this information? How do you use this information about the paradox of life to make your life better? Because again, this life is called life skills, and just understanding life is a skill, but how do we use it to benefit our lives? Okay? So the quality of the life that you live has a lot to do with life being long. Again, the quality of the life that you live has a lot to do with the anticipation that your life will be long. People who are homeless for their entire life struggle in many ways that perhaps could have been avoided, not always, but perhaps could have been avoided if they made different decisions when they were young. So I have worked with many homeless people over the years. For the past 20 plus years, I was working in homeless shelters, and I've heard many people's stories. And not for everyone, but for many people who are homeless, they would have lived a life where they were largely not homeless if they made different decisions when they were young. If they had made better decisions when they were your age, again, perhaps they wouldn't have lived, the 60, 70 years of the homeless life that they lived. Perhaps they would have lived a life surrounded by family and friends and had an easier time of life. And so again, the quality of life that we lead depends a lot on us anticipating the fact that life is long. If you live every day like it were your last, which is a popular saying, then you will not prepare for life being longer than a day. And so while people who say that, people who say, oh, you should capture every moment and live it like it's your last moment on earth, what they mean to say is that you should live without regret, and you should live in the excitement of the moment and feel what is happening around you. And they're right, because life is short. But remember, the paradox of life is that it's also long. And so at your age, it's important that you begin making decisions anticipating the fact that your life will be long. Begin building character. Begin practicing patience, because your life will most likely be a long time. Patience is not something that people are born with. Patience, just like any muscle or any skill, is developed and built up over time and over practice. Patience is a skill that you and I can learn because life is a long time. And so, again, I definitely do not look at these days, and I'm aware of that. But when I was younger, I was actually quite athletic. And when I was younger and more athletic, when I would want to be focusing on a certain muscle group or a certain skill, I would have to exercise that muscle group, and I would have to do different methods of training. One method of training that is terrible for your joints, and I actually don't recommend, that I picked up from a cartoon, was wearing weights and doing exercises with your weights on your ankles and weights on your wrists. And so I was a black belt in Taekwondo, and after watching too many Japanese cartoons, I thought it would be a clever idea to practice my kicks. We had to do 1,000 kicks in a day. Oh, I shouldn't touch my face. We had to do 1,000 kicks in a day. And I decided that it would be good to wear ankle weights and do my kicks with ankle weights. And although that is a terrible thing to do to your very poor joints, it did make my kicks stronger and faster. And I was much more athletic. I could jump higher. I had more endurance because of that training. And so in the same way, you need to consciously train yourself to be patient. Train yourself to control your anger. Train yourself to not yell at those around you. Because again, the people that we love are the people that we hurt the most. Oftentimes, the people that we care about the most, that we live with every day, are the people that we can be the least patient with and the least understanding of. And so, because life is a long time, the way that I want you to use the paradox and knowledge of the paradox of life today is to begin to practice patience. This is something that you can do right now as you're stuck at home in quarantine. Begin to think about the ways that you are impatient with others. Maybe a family member, maybe a neighbor. And I want you to try to be more patient with them. Both for them, because you'll make their day better, but also for you, because you will make your life better. Because your life is going to be a long time. And if you begin to master the skill of patience at a young age, the quality of that long life will be much greater. Thank you, and have a great one. We'll get on to the rest of our subjects now. Hello, and welcome back to Current Events.
Hi, guys.
Miss Kimmy's over here still. I'm over here still. This is week 2,
Having a
day
Snickers
4.
bar.
You really have a Snickers bar?
I do.
Oh man, I'm jealous. I stole some Cheetos from you the other day, though.
That's
So
okay.
I should probably let
Do
you
you want
know.
one of these too?
You have an extra?
I do.
Oh boy. All right. Pause. Okay.
It's that
All right. Welcome back for week 2, day 4.
Okay.
Thank you, Miss Kimmy.
Yeah, sure.
There's like a glare, actually. Anyway, new vocabulary. Okay. We talked about liquidity. And then the other day, from a question from Miss Kimmy, we talked about the concept of scarcity. Okay. Oh shoot! I have to spell things correctly because Miss Kimmy's
Yeah,
here.
I am.
Did I get it right?
Those are great.
All right, perfect. See?
Scarcity, yes.
Look at that. I'm not a terrible speller all
Not
the
at
time.
all.
All right. So, liquidity. The ability of something to be sold I would say turned into liquid money. Okay, can you guys still see that there? It's like right at the edge of the board. Liquid money here. Turn this just a little bit. There we go. See, I put a mark on the board. I kind of marked where you couldn't see anymore. Okay? All right, let's talk about scarcity. Okay? And now, scarcity is the idea that something is worth something because people want it, and it is, what's a good way to say
It's
it?
in demand.
It's in demand, okay? So it's in demand, people want it, and there's a limited supply. That's what I was trying to say. So it's in demand, people want it, and there's a limited supply.
Supply and demand.
Scarcity. Things are valuable. Because they are in demand and there is a limited supply. Okay, let me give you a good example of something that is, for all intents and purposes, completely worthless, okay? But for a while was very expensive because of this idea of scarcity. The fidget spinner, okay? So kids, fidget spinners are nothing but a ball bearing. Okay, it's a ball bearing inside of a little piece of plastic, and some fidget spinners have maybe 4 ball bearings inside a little plastic shell, okay? Those are almost completely worthless, okay? If you go to skate country and take some of those ratty old rental skates that they have that have been used for years and they're about to throw away, they would probably give it to you for free. You could take the skates apart, you could take 8 ball bearings out of those, and you could make several fidget spinners. Okay, because a fidget spinner is just a piece of plastic and a ball bearing that is almost no value whatsoever, okay? But because people wanted them, okay, they only had value, so they had value, okay, because they were in demand, and again, no real practical purpose for them, okay? They were in demand just because people wanted them, and there was a limited supply, okay? Because of the scarcity of the fidget spinner, because of the limited supply and the fact that people wanted it, even though it had almost 0 practical value, this idea of scarcity made them very expensive. My son, who was I think 4 years old at the time, the very first thing he ever purchased with his allowance money was he went to the store and bought a $25 fidget spinner. And I was not impressed. I thought that was a terrible life choice. And I told him as much, but I didn't want to ruin the moment because he was just a little kid spending his first money at his store, giving it to the cashier, and it was adorable. But again, that fidget spinner that he paid $25 for probably took them less than $1 to make. Almost no value whatsoever, and he doesn't even play with it anymore. And the only reason why they could charge that outrageous price and kids were buying it was because of this concept of scarcity, okay? There's a limited supply of something, even if it has no practical value, people want it, okay? For the generation before you, or maybe 2 generations before you, I don't know, Miss Kimmy and I remember something called a Pog, okay? And maybe you guys have heard of them, okay? Pogs were these little tiny round pieces of cardboard that people, my age growing up, went crazy over. You would have entire kiosks at the mall that would just sell Pogs, which were just round pieces of cardboard.
Yep.
And they originally came from this idea in Hawaii where they would put the little milk. You get a bottle of milk, and the bottle of milk at the very top would have a round piece of cardboard that would seal the milk in, and kids would take them off and play with them. And for some reason, they got popular. And so people were literally paying $10, $12, $15 for a tiny round piece of cardboard with a picture on it. No value whatsoever. Because of the idea of scarcity, people were willing to pay stupid prices for them. Okay, and so this idea again of scarcity, okay, makes things valuable that otherwise would have no value. One last example.
Pet
okay.
rocks.
Yes, exactly. That's where I was going. Oh, it's like we're the same person
Chia
sometimes.
pets.
So, well, okay, chia pets. You get the little chia thing, and the commercial chia. All right. Anyway, you kids don't know what we're talking about. If your parents are listening, they might be laughing at us. That's okay. All right. The last idea. the last example is the pet rock, okay? There was literally a company, some man who is probably very rich somewhere on an island, a genius of sorts, invented the idea of the pet rock, and it is exactly what it sounds like. People would go to the store and they would buy a beautiful package. It was shrink wrapped with like plastic packaging around it, and inside this beautiful package would be a rock. A normal, everyday rock. But it was a pet rock. And so they could buy the pet rock. And then what's more than that, these pet rocks started selling for a lot of money. And you could even pay to send your rock on vacation. Did you ever do this, Miss Kimmy?
God, no.
So you could pay.
But I've heard of people that did.
People would actually pay $100 to take their pet rock, okay? Oftentimes these rocks, this is a real thing. I'm not making this up. These were little rocks, and I think they usually had googly eyes on them, didn't they? It was just a little rock with 2 googly eyes glued on the front. And it was a pet rock that people would pay all kinds of money for. And you could pay $100.
I mean, they were rare.
And you could ship your pet rock to a pet rock vacation for $100, okay? And your pet rock would go on vacation, to the beach or to the lake or to the mountains. Again, this is a real thing, not making it up. And what they would do is they would take your pet rock and they would put it with other pet rocks that were on vacation, and they would take photographs of all the rocks on vacation having fun together. For real. And then for $100, you would get your pet rock back in a week or two, and there'd be photos of your rock having fun with other rocks. No value whatsoever. And some guy and his family are rich now because of it, okay? And it goes back to this idea of scarcity. The only reason why the pet rock, the pog, or the fidget spinner were worth any money was because of the idea of scarcity. People wanted it, and there was a limited supply, okay? And so, why did we introduce this idea? Well, $1, okay? The United States dollar is worth something because of the idea of scarcity, okay? It is worth something not because it has any kind of intrinsic value. You can't take a $5 bill and eat it for a fulfilling meal, okay? You can eat it, okay? I think some of you have eaten it from the way I've seen you relax on the couch, okay? Again, looking at you 7th and 8th grade boys. But you can't actually eat a $5 bill and have it give nutrition to your body in a way that would sustain you. There's no value in that $5 bill. The only reason why it's valuable is because there's a limited supply and they're in demand. People want them, okay?
Yep.
And so that is the end of today's lesson. Tomorrow we're going to learn a new word called inflation, okay? All right, on to history. All right, ladies and gentlemen, we are in Civil War history, week 2, day 4. So for today, we don't have a new lesson. Today is a review day because tomorrow I'm going to be giving you the test in the download. So for today, please go back through your Khan Academy, rewatch any videos that you feel maybe you're a little bit weak on. If you're in my class, you have a full history book you can take a look at. Tomorrow I'm going to be posting the test. And so today, your homework for today is to take a few minutes and review for that test. All right, thanks. All right, literature, week 2, day 4, a massacre. In this chapter, Captain Nemo shows his true brutality. And Aronnax, for the first time, actually, for a smart guy, it's taken him really long to get here, but he really begins to fully comprehend that Nemo is a warrior out for revenge. Again, not this staid scientific man that he at first believed that he was. And so I don't remember if it was in this chapter or the chapter before, but Aronnax reveals that his wife and children were all killed and everything was taken from him, which has pushed him to the brink. And because of this desire for revenge, he is a little nuts, to put it plainly. And so the ship of unknown origin that is a warship is coming towards them, and Captain Nemo is letting it gain on them. And Ned Land and Conseil and Aronnax are all, for some reason, they're being fired on, and the three of them think it's a really good idea just to hang out on deck, even though cannons are being fired at them, and they're talking this through. Ned notices that the ship is a warship because it's plated in iron. Remember, in the American Civil War, we saw the first ironclad ships, and this is 5 to 10 years later, and so the ship is absolutely an ironclad ship. But oddly enough, this ironclad ship doesn't have reinforcements on its bottom, on its underbelly. And so on its underbelly, it's vulnerable. And that totally makes sense, doesn't it? Because if you were to retrofit a ship that wasn't already constructed from iron, there's no reason to put iron plates underwater because that's not where the cannons go. Like if you're fighting another ship with cannons, the plating has to be like up top and not underneath. And so this ship is like vulnerable at the bottom. And so as the three of them are talking, Nemo comes on deck and he was like, all right, we're going to do this. Let's sink it. And Aronnax is like, don't do it, man. And Nemo's like, I'm totally going to do it. So shut up and head down. And so Aronnax actually does what he should. And so in a moment of sanity, Aronnax and his three friends all go underneath and they kind of wait for it to be over. And so the Nautilus dives deep. The Nautilus cuts through this other warship like butter. It hardly, I think it says something like it doesn't even like make any waves or something like that. And then they watch out the window with Captain Nemo as the ship sinks underwater, and they can actually see the sailors like trying to get out. And then at some point there's like a big explosion, and it's like this horrifying scene, and Captain Nemo's just there and he's watching it like. It doesn't even say anything. He just kind of walks away, you know. And then Aronnax like follows him and he sees him in his room, and he's like crying, you know. And somewhere along this line, actually, I think at the beginning of the chapter, Aronnax already realizes, hey, you know, my hope for exploring the seas with this guy and writing this amazing book and doing all this science, those hopes are kind of foolish. This guy is nuts. And we got to get off this ship. In fact, when the three of them are up on deck, kind of like talking about the ship coming up, they were like, we're going to sink that boat, but we would rather be on that boat when it sinks than this boat, or this Nautilus, when it's sinking it. And so Aronnax, I think, even feels like a certain amount of guilt for being on the boat, or on the Nautilus. Just even being there, he kind of feels like he's part of the crime, you know. And so it is time for them to leave. Aronnax is ready. You know, up until now, Aronnax has been like, I don't know if I want to go. This is the chance of a lifetime. But now he's like, hey, man, we got to go. We got to scram. This is really bad. There's no way that we can stay. And at this point in time, too, you know, Captain Nemo, he's a lot more human, right? Like he is... he's not this like mystery figure that nobody understands. Like we get exactly why he's doing what he's doing. He's doing it out of revenge, out of a bloodlust. And Nemo, as he begins to act on these revenge or these vengeful thoughts, he kind of gets not moody. Yeah, maybe moody. He gets moody where he's like kind of dark, you know. And Aronnax realizes that this has probably happened before, because they were drugged once, and they were drugged and put to sleep in their room with like the doors locked, and he figures that they were probably sinking another ship during that episode too. And so anyway, that's where we leave our characters, with this horrifying realization that boom, you know, they just sunk another ship and they watched all these people go down and probably die. And yeah, whew. So that was the chapter, A Massacre. So, let's see here. Tonight, the chapter that you're going to be reading, let me look it up here, Captain Nemo's Last Words. Chapter, the penultimate chapter. Penultimate means second to last. And so we only have 2 chapters left, guys. And so this is it. The end of 20,000 Leagues Under the Sea. And finding out what ultimately happens to our 3 friends and the dear captain. All right, ladies and gentlemen, today we're doing science class, and right now it is week 2, day number 4. All right, so at the beginning of the week, you received a handout worksheet, and that handout worksheet is for all of this week and all of next week. So as I was thinking about it, I think there's kind of no rush. I want you guys to really understand these concepts very clearly before we just move on. I don't want to just kind of rush through it to rush through it. And these are some pretty fundamental things that will kind of follow you for the rest of your life because they're basics of physics. And so Newton has three main laws, and they are easy to remember if you just kind of break them down. Okay, and so Newton's first law of motion that we've learned already is the law of inertia. Okay, you can think of inertia, you can think of momentum. It's the one that says objects at rest tend to stay at rest, objects at motion or in motion tend to stay in motion. So that's law number one. Law number two is the law of force. Okay, so force equals mass times acceleration. So the first one is inertia. The second one is force. Newton's third law, which we haven't learned yet, is the action-reaction law. For every action, there's an equal and opposite reaction. Okay, like you know, when you see the pendulum, boom, that kind of deal. Okay, that's Newton's third law. Okay, and so again, inertia, force, and action-reaction. So again, I want you to really kind of have these processed and understand them. It would be fantastic if you could memorize them, if I could call everybody on the phone and be like, tell me Newton's three laws, and you'd be like, inertia, force, and action-reaction, and I'd give you an A. But that's probably not going to happen, given just how busy we are and everything else going on. So we are going to review Newton's first law today. We will review Newton's second law on day 5, and then on next week, on week 3, day 1, we are going to be doing, I guess, a lesson on gravity, and then we are going to be moving forward with Newton's third law. Okay, so I found this delightful video in the Creative Commons, and it is from this wonderful nonprofit called Fusion Education. Let's take a look.
You should already know what we mean by an object has a velocity, and what we mean when we say an object has uniform motion. If not, you may want to check out this video first. In this video, we're going to look at how the velocity of an object depends upon the forces acting on it. In physics, we have 3 fundamental laws of motion, created by Sir Isaac Newton way back in the 17th century. Today, we are looking at the first law of motion, sometimes called the law of inertia. Newton's first law says that an object will remain at rest or in uniform motion in a straight line unless acted upon by an unbalanced force. But what does this actually mean? Firstly, it means that when an object is not moving, it will remain at rest until an unbalanced force acts on it. The statement also tells us that an object will remain in uniform motion in a straight line unless acted upon by an unbalanced force. Take a look at this ball here. As the child kicks the ball, they exert an unbalanced force on it, changing the ball's velocity and causing it to move. But as it rolls along the ground, the ball will slow down and will eventually come to a stop. Because the ball is slowing down, we can say that its velocity is changing. By Newton's first law, this means that the ball is experiencing an unbalanced force. In this case, it's the force of friction that opposes the motion and eventually stops the ball. Note that there is no forward force on the ball. She is no longer kicking the ball, so there is only backward frictional forces which slow the ball to a stop. Look at the diagram of the aeroplane shown. If the thrust of the engines is equal to the drag force, it will move forward at a constant speed. The plane will travel at constant height if its weight is balanced by the lift force from the wings. We have uniform motion. If the plane wants to move faster and increase its velocity, then the thrust force pushing the plane forward needs to increase. It becomes larger than the force of air resistance and creates an unbalanced net force. The plane now accelerates, no longer moving with uniform motion. Drag increases with velocity, so very soon the plane will have balance but larger forces again, and its velocity remains constant but higher than before. Quantitatively, we can find the net force of any object by considering the size, or the magnitude, and the direction of each force acting on an object. It can help to draw on the forces yourself. Take a look at this example here, which shows 3 forces acting on the object. The 2 vertical forces are equal and opposite, therefore cancelling each other out. However, the horizontal force has no opposition, and so it remains unbalanced. This means that the net force will act to the right, and will have the magnitude of the horizontal force. When working out the net force, it's a good idea to consider the horizontal and vertical directions separately. At the end, these directions can be added up to give you a diagonal force. You can think of these forces to be a bit like points on a compass. If we add together north and east, assuming the forces are equal, we will get a result of northeast. Now you try. What direction do you think the resultant force will be here? Pause the video and have a go. The resultant force is obtained by drawing lines parallel to the forces to make a parallelogram or rectangle. Well, first of all, we need to find the resultant horizontal force, like this. Then, we need to draw the lines parallel to the forces to construct the resultant force. Did you get it right? To recap, Newton's first law of motion, the law of inertia. Objects will keep doing what they are doing when they experience no net force. They will continue to move with uniform motion or remain stationary unless an unbalanced force acts on them. This unbalanced force will cause them to change their velocity, speed, and/or direction, which depends upon the size of the direction of the net force. If you want to see how we calculate these net forces, then watch our video on Newton's second law of motion.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any questions. Why not check out our FuseSchool app as well?
That's awesome. Okay, whoops, where'd we go? There we go. So I definitely recommend you check out the Fuse School. They are really cool, and just like our school, Da Vinci Tree, they're all nonprofits. Everything they do is in the Creative Commons. Good people. So anyway, that's it for today. Again, hope you enjoyed the video on inertia. Hope you learned something, or at least reviewed something, so it's like in your brain a little bit better. Let's move on to math. Is group 1, week 2, day 4. Okay, so here's what we are doing for day 4 and 5 for week 2. On day number 4, we are going to be taking a look at another worksheet today for our homework, but today's worksheet is a little bit different. Yesterday's worksheet, we did only trapezoids, and we had them with decimals. Today's worksheet, we're going back and we are reviewing everything. We're reviewing how to do area of rectangles, area of triangles, area of circles, and area of trapezoids, and we're using decimals. Okay, so we're doing all of it. Okay, the thought occurred to me yesterday after I finished recording your video that you should be multiplying with decimals already, because we did circles, and that uses pi, 3.14. However, you could have been using 22/7. Either way, I don't mind. It's all good. And then on day number 5, we are going to be introduced to the concept of the Pythagorean theorem. The Pythagorean theorem from a guy named Pythagoras. And it's this really cool triangle thing. So Pythagorean theorem is tomorrow, and that's, if you've ever heard of it, it's kind of cool. It's a squared plus b squared equals c squared for all right triangles. So let's get to today. Before I cut you loose to do this worksheet today, I wanted to do a quick review of everything, and I know hopefully you're sick of this by now. My goal is to really like ingrain it in your soul so that you never forget how to find the area of a triangle, rectangle, circle, and trapezoid, because for the rest of your life, you're going to need to be able to do this. So let's take a look. Oops, wrong one. Just for tomorrow. Ah, okay. Here we go. Okay. What is that? Oh, no, it's a 0 up there. Cool. All right, so review. And this is group number 1, day number 4, week number 2. I usually put week before day, but all right, it's cool. All right, so we need to find area of rectangles, triangles, circles, and what is it? Trapezoids. We should also think about parallelograms again. We haven't done that in a while. Parallelograms. Okay, so, oh, is my dog there? Oh, he's there. Let's see him. I think he's kind of shy. There he is. There's my wrecker of screens. Okay. Anyway, whoo. Okay, so back to math. When we're doing the area of a rectangle, again, it's just the length times the width equals the area. Okay, so if we have 2 and 3, it's just 2 times 3 equals 6. Okay, all right, when we're doing triangles, it's the height times the base times 1/2. Doesn't matter which one comes first, it's all good. Okay, so if the height is 3, the base is 4, 3 times 4 times 1/2 gives us 6. Okay, oh, I didn't mean for that to both be 6. Okay, for circles, the area is pi times the radius squared equals the area. Okay, so if we have a circle, okay, and the radius is 2, we have to take pi, which is 3.14, times the radius squared, which would be in this case 4, because it's 2 times 2. 3.14 times 4, 16. 4 times 4 would be 5. 3 times 4 would be 12. 12.56. And so the area would be 12.56, just like that. Okay, remember, bump the decimals twice there, twice there. Nice. Okay, for trapezoids, okay, we combine. I'm going to bring it down a little bit. We combine rectangles and triangles, remember. It's the same thing as rectangles and triangles, but both of them together, okay? So if this is, let's say this is 7, this is 10 on the bottom, and we have a height of, let's say 4, okay? So I'm going to use my colors again. I have this rectangle in here, which would be 7 times 4. Okay, and then over here, I have this triangle here, and this triangle here. Make a separate triangle like that. The base of 3, and a height of 4. So I take 1/2 times 3 times 4. Okay, and so that gives me 6, because these two are 12, and then times 1/2 equals 6. And then this up here, 7 times 4 is, what is it, 28, yeah. Okay, got 28, and you just add them both together there, 34. Okay, so 34 units squared. Okay, and that's how I do that. That's my answer. Answer there, answer there. 12. Okay. All right. Lastly, for parallelograms. Okay. Parallelograms, everything is parallel. Okay. Let's see. If this is a length of 11, if this is a length of 6, it doesn't matter what length that is. It matters how tall it is. Okay. So do you see here? The height is 5. Okay. And so this length does not matter. And the formula for this is just the height times the base, just like a normal rectangle, okay? And so in this instance, My height is 5. My base is 11. Gives me 55. Okay, that's it. Oops. Okay, so that's it for today's review. Go ahead and download the worksheet and get to work on your homework review worksheet that's kind of like covering the area of all these different things that you should be remembering. Okay, all right, see you tomorrow for Pythagorean theorem. I just finished filming yesterday's day 3 lesson for group 2 kiddos, and what was I going to say? I left one problem undone. So we're going to do that one problem. Then I have a worksheet with just like some systems of equations that I would like you to solve, and then you're done. So today it's going to be kind of quick. We're just making up for the one problem we didn't do yesterday. I think it's only one. Let's check together. Oh, that's my iPad. Okay, here was the problem yesterday with Lucy and her big brain solving of this. Here's the one problem that we're doing together today. Amber, Allie, Tegan, Riley, and Hazel start an environmental club. They planted a 16-inch hemlock tree that grows at a rate of 4 inches per year. Then 5 years later, when they're still friends and out doing cool BFF things in college, they planted a 10-inch blue spruce tree that grows at a rate of 6 inches per year. Side note, for an environmental club, having only planted 2 trees in 5 years, maybe they're not doing so well. Anyway, in how many years after they planted the hemlock tree will the 2 trees be the same height? How tall will the trees be? And so just to kind of like throw this down really quick, kids, so the hemlock tree kind of grows with a curve like this, okay? And the blue spruce tree kind of grows with a curve like this, okay? And so the 2 are going to overlap at some point in the future, okay? Kind of like that, all right? So we need to do the math. All right, so the 16-inch hemlock tree grows at a rate of 4 inches per year. So we need to use this information to put this into a y equals mx plus b. So they planted it, and it was already 16 inches, okay, and it grows at a rate of 4 inches per year, okay? So hemlock, so it's already 16 inches, and it grows at 4 inches per year, okay? And then we have it was 5 years later, and there's 5 years. 5 years later, okay? And then we have the blue spruce, okay? The blue spruce grows at a rate of 6 inches per year, okay? And it is 10 inches. 6 inches per year, and it's 10 inches, okay? So 10 inches, this is the blue, I don't know, I capitalized that, and not the other one. Blue spruce is 10 inches, and then it's 6 inches per year. Okay, so here's the deal, all right? So this hemlock not only was taller, but it has a 5-year advantage. So all of this information up here goes with our hemlock tree, okay? And so as you may have already guessed, kiddos, the 4 inches per year, that's going to be our slope, okay? And then this 16 inches plus whatever this is down here, that's going to be our plus, okay, or our y-intercept, or our b, I'm sorry, our b. So for our hemlock, the equation is going to look something like y equals, it's grown at a rate of 4 inches, so y equals 4x plus, and here's where it gets a little tricky. Again, it already was 16 inches, and it's been growing for another 5 years ahead of time before the other one, okay? And if every year it's growing at a rate of 4 inches for 5 years, okay, 5 years times 4 inches per year equals 20 inches, okay? Now it's grown another 20 inches, and it was already 16 inches. So now we have to take 20 plus 16 inches, add those two together, we get 36 inches, okay? So our b in the y equals mx plus b is going to be 36 inches. Okay, so hemlock tree is y equals 4x plus 36. Okay. Now the blue spruce is explanatory. We'll call it the blue spruce, so I don't have to call it the BS tree. Ooh, nobody wants a BS tree. You want a blue spruce tree. Okay. All right, and so that is 6x, because it's growing 6 inches. It's going to be plus 10. Okay, and this is a system of equations. Okay, and so the question is asking us when the trees will like meet up, right? Is that right? Okay. In how many years after they planted the hemlock tree will the two trees be the same height? Okay. Oh, they're throwing like a wrinkle at us. Okay, they want to know the hemlock tree. So with these equations here, okay, we can tell you how far from the blue spruce tree. So we have to make sure at the end we have to add another 5 years, okay? Add 5 years in the end. I'm going to make a note for myself. Those of you who've been with me for a while, y'all know that I need these notes for myself. Add 5 years in the end. You're like, Mr. World, didn't you write these problems? Well, I kind of just stole them out of the book and changed things. So, all right, okay. So here are our two equations. As always, if there's a way for me to be lazy, I will. So let's plug these equations into our graphing calculator. So start with the top one. Y equals 4x plus 36. Okay. What is up there when I do that? Oh, there's a bunch of pictures of me. Oh yeah, those are other videos I recorded for you guys. Some Netflix and some Hulu going on there. Come on, guys. Don't pretend like you don't do it, too. Everybody watches Netflix. Some people watch Hulu. Everybody watches YouTube. You're watching YouTube right now, in fact. Okay, so we have y equals 4x plus 36. Pop that in there. Oh, I never shared what we're using for a graphing calculator, 4x plus 36. It's called GeoGraph or something like that. Yeah, Graphing Calc. If you just type in Graphing Calc in your app store, you should be able to find it, and it is free. So y equals 6x plus 10. Okay. Oh no, I'm getting another phone call. Error last time. Okay, there we go. All right, y equals, can you guys still see me? Yes, you can. Haha, victory. Y equals 6x plus 10. Y equals 6x plus 10. Good. Okay. All right, and I can see nothing because my window is still way off from yesterday's question. Where is the thing that readjusts your window automatically? That would be cool. Settings, graphics. Wait, is it zoom to fit? There's got to be a quicker way to do zoom to fit. Somebody send me an email and tell me, okay? Because that's a lame way to do it. Okay, wait, do I do this? Yes. Okay, cool. All right, so we have our two trees here, okay? We have our first tree, which is the hemlock. We have the purple tree, which ironically is the blue spruce. And they intersect at 1388, okay? And so 13 right there on my x-axis, I'm assuming that that's the years, because if we look back here, okay, x is how much they grow every year. You all see that? Okay, so x is how much they grow every year. So in my graphing calculator, x would have to be the years. So they're going to meet up with each other at year 13, and they're each going to be 88 inches tall. Okay, so they meet up at year 13. So meet at year 13. Y equals 13. Okay. However, remember we made this note because it says how many years after the hemlock tree. Okay. Oh, the phone call messed up my thing. Okay. How many years after they planted the hemlock tree? And the hemlock tree was 5 years before the blue spruce. Okay. So it needs to be then 13 plus 5. Okay. So let's go 13 plus 5. Hooray, 18. We got it. We did it. Year 18. Year 18. The hemlock tree is old enough to graduate high school. Okay, cool. All right, so ladies and gentlemen, that is going to be it for, what day is it? Day 4. Go ahead and download the PDF. Now, the PDF does not have word problems. It just has some basic systems of equations for you to work on. And then tomorrow's PDF is going to have some systems of equations for you to actually like sit down and do. Okay? All right, so get them done. Email me if you have any questions, mroll@davincitree.academy. I will probably have a baby by the time you're seeing this. And so I would also email jbarbero@davincitree.academy. Did I say .com? At davincitree.academy. And hopefully he can answer your questions. Okay? All right, everybody. See you later. See you tomorrow. Oh, what do I press? Oh, it's up there.